Hello, and thank you for joining this presentation entitled Functional Locking Through Omission from HLS to Obfuscated Design. My name is Benjamin Carrion Schaefer, and I'm an assistant professor at the Department of Electrical and Computer Engineering at the University of Texas at Dallas. This work was jointly done with Professor Yorgos Makris and two of our students, Zi Wang and Sayam Mohammed. We have seen that the magnitude of economic impact on the electronic industry due to IP violation alone has been estimated to be around $2 to $4 billion already in 2012, and things are getting much worse. Hardware accelerators are common and are often the differentiating component in modern SoCs. And the implementation of these accelerators is the main competitive advantage. So companies need to make sure to be able to protect against IPs being either reverse engineered, overproduced by untrusted fabs, or the unauthorized usage of these accelerators. So in this work, what we propose is a method that efficiently locks circuits generated from untimed behavioral descriptions for high-level synthesis using embedded eFPGAs. So let's look at an overview of functional locking. So functional locking prevents a circuit from working as specified if the key applied to it is not correct. And there are two main forms of doing functional locking, right? One is to add extra circuitry as shown in the figure on the left-hand side by adding extra keys. If the logic key is not correct, then the primary outputs will not work as expected. Now, a second method of locking that was recently introduced that we called locking through omission is basically extracting a portion of this digital circuit onto an eFPGA. And now the bitstream of this eFPGA actually acts as the locking key. The main problem, obviously, with this approach is that the large area and timing overheads. And this is what this work deals with, and basically how to minimize the overhead associated with the portion mapped to eFPGA, and basically be able to generate a circuit that has exactly the same timing as the ASIC-only implementation. So this is an example of the proposed flow. The input is the C description on the left-hand side here with the hardware accelerator that will be synthesized using high-level synthesis, a target frequency, in this case 100 megahertz, and a technology library. The high-level synthesis process, a typical high-level synthesis process can be subdivided in three steps. The front end that does the technology-independent optimization and builds the CDFG out of the C description. Then the main HLS steps that does allocation, scheduling, and binding. And finally, the back end, which basically outputs the Verilog. We see here that in the left-hand side of the C code, high-level synthesis vendors make extensive usage of synthesis directives in the form of pragmas. These control, for example, how to synthesize loops that can be fully unrolled, partially unrolled, and so on. Based on how we set those pragmas, the HLS parser will create a different CDFG, different graph based on these options, and we see it here in figure C. So the main goal here is to determine which portion of the CDFG to map onto an eFPGA, such as the scheduler, right, creates the same schedule as an ASIC-only implementation. This means that we need to look at the slack available in every control step, and based on the security metric that we're going to introduce later, determine which portion of the C description to map onto an eFPGA. And we see here on the right-hand side that obviously the area overhead will increase due to the use of eFPGA, but the main goal is to actually make the latencies exactly the same between ASIC and ASIC with eFPGA. So this is an overview of our detailed proposed flow. The inputs are the C description of the hardware accelerator, the technology library of the ASIC and the eFPGA, and we can have a library of pragmas that we want to use in our case. So the first step is actually selective partition of the data flow graph into the ASIC part and the eFPGA part. So for that, the first step does a high-level synthesis of the entire C description, targeting only ASIC. Then after the scheduling step, we can do the delay of every control step, and we can extract the slack available, the timing slack. Based on that and the security, the amount of code that we want to map to the eFPGA, we partition the CDFG into the eFPGA portion and the ASIC portion, and then we synthesize them, first the eFPGA, and then we combine everything together, guaranteeing that the latency, the number of control cycles are exactly the same. A second step is then the regeneration of this by setting a new set of pragma that generates a new CDFG, and then we can do a new partition. This will allow our method to create a trade-off curve of Pareto optimal partitions, like shown here in this figure. Let's look at the security analysis. What do we mean with security? So design obfuscation methods typically aim at protecting against adversaries that have access to a fabricated IC implementing an obfuscated design, and have black box access to an unlocked fully working chip. This is typically the Oracle. In both cases, the adversary can typically use either a brute force approach by trying all the combinations of the keys, or a more modern attack is what's called a SAT attack that has shown to be a much faster way of finding the key. Now, the advantage of this locking through omission is that the adversaries require the logic function of the obfuscated portion of the circuit, but in obfuscation through omission, that is not available because the bit stream is not there. For example, the factory that wants to reverse engineer the chip doesn't have access to the bit stream that configures the FPGA. Now, to test our security, the security of our method, we created a model where we have implemented the ASIC as the gate net list and the extracted portion on the eFPGA. So we synthesize the ASIC portion using design compiler into a gate net list. We have the FPGA portion where we create a model of the eFPGA that can be programmed through a bitstream generator. And then we assume that the attacker knows the eFPGA bitstream format. So you see in the figure, the attacker can create different valid bit streams, download to the FPGA, configure the FPGA portion, and then test if the functionality is correct or not. So now this is the model at which we try to break our system. Let's look at the experimental setup. For high-level synthesis tool, we use NEC Server Workbench. For logic synthesis, design compiler, you see the specification there, the computer platform. And for the evaluation, we choose different 8 benchmarks from the open source S2C benchmarks. And we compared our method versus another method that does a similar approach, but does the partition instead of at the DFG level, at the C level. So basically, they map different portions in the C code directly to the FPGA. So these are the results. In terms of timing overhead, the delay obviously increases. We compared the ASIC only versus the previous work that does the extraction at the C level versus our proposed method that does the partitioning at the CDFG level. And obviously, in most cases, the delay increases by 14%. But the most important thing is that in all cases, in our case, we always able to meet the target synthesis frequencies of 100 megahertz. So that means that our method never increases the latency of the circuit because the scheduling steps are kept. Whereby previous work actually increased the latency because they did the partition in the C code. In terms of area overhead, the average was 1.7 times because obviously we use the eFPGA instead of just ASIC only. And in terms of the runtime, our method versus the previous work, our method is slower, 1.82 times slower, basically because we have a larger search space, but it's still manageable. It only takes on average 11 minutes for the largest benchmark, which is the CNN in this case. Let me summarize what we've presented in this work. A method to efficiently lock behavioral IPs through omission. So the key features is that we use an eFPGA as a locking mechanism, and now the bit stream acts as a logic key. You can think already that the number of combination grows more than in a traditional locking mechanism because the bit stream encodes the functionality of the FPGA plus the routing as well. And we have shown experimental results very quickly that our method is very effective, leading to smaller area overhead than the state of the art. One important thing that I've stressed this a few times, while keeping the original timing intact. With that, I conclude this presentation. You can find more details in the paper, and I would like to stress and thank our sponsors that this work was partially sponsored by the NSC IU CRC Center for Hardware and Embedded System Security and Trust through Project P720. Thank you very much, and I'm happy to take any questions.